Hey everyone, welcome back to the next part in our series with Professor Michael Meyer from the University of Michigan. We talk about instrumentation, the current search for exoplanets in the universe, and the Decadal Survey held in astronomy. If you're new to our podcast, make sure to check out the last part in the series from last Friday, and the final third part will be uploaded next Friday. Hope you enjoy.
So the probability of biochemical origin of life in the universe.
Before we get there, though, presumably there's going to be massive work in improving our methods of detection, our observational methods, our statistical methods, our computational methods. And I know that, and you briefly mentioned that you were interested in instrumentation. Could you kind of explain how the field of instrumentation, and this particularly the part that you're involved in, has evolved with the advent of the computer technological era? Because I think, at least from our perspective as students, computers have enabled a lot of things to come down and to be far more accessible by everyone. But on the other hand, I assume that computers have also enabled the upper ends of science to progress faster and better than they would have before. So could you kind of explain your role in instrumentation and all of that kind of stuff?
Okay, so instrumentation, when I started graduate school, and maybe it was even unique for that time, but I had one of my supervisors was very much a tabletop experiment person. I don't consider myself an instrumentalist in the way that I consider Professor Monnier, John Monnier in our department, one of these world-leading experts in his specific technique. And my old supervisor was like that. I joke that he could go into a garage, basically all by himself, and come out with like an astronomical instrument, because he could do the wiring, he could do the electronics, he could do the optics, he could do the computer programming. I mean, he could do everything. I'm not like that. I'm much more of a tinkerer. I like to come in and recognize a new application or an augmentation to some other existing technology or instrument that can enhance. And the reason I'm really passionate about that is because I really want my field to make rapid progress towards the answers that I am just, I mean, the thing that drives me is I just want to know the answer. I just can't stand not knowing the answer. And so if I can help make a little widget that will get us closer to the answer faster. I also tell people at heart, I'm just basically lazy. So if you told me I had to take a little pebble and like push it up my nose with my nose up a mountain for like 10 years, or, you know, you could go into this laboratory and make this pebble nose pushing widget and it could happen in like a week. I'm totally going to go do that, you know, because I can't wait. I'm impatient. So, okay, so instrumentation, when I started, my professor was really good at just enabling us to, here's a detector, here's a 0.4 meter telescope, design a spectrograph for it. Okay, so then you scratch your head and I'd open a bunch of textbooks. And this is, again, a thing where I learn by doing. So in the last 20 years, a lot of our educational innovations have come from recognizing that inquiry-based discovery is an important tool for you to absorb deeply in your physical intuition and your worldview, concepts of physics and math that you're learning at a lecture in a classroom. And that was very natural to me because I did most of my learning arguing with my fellow students in a late night laboratory study session, or in a laboratory actually building things with my hands. That's where I really got it. So those things resonate with me, which is why I love teaching Astronomy 361 so much in our department. So in the early days, it was much easier for instrumentalists to build their own things. They didn't need that much money. Even back then, it was a lot of money, but $100,000, you could kind of build a camera for that in the 80s and 90s. Nowadays, as we get up to 8-meter telescopes, 6.5-meter telescopes, the instrument budgets are millions. I just had a grant approved for order that to build a new camera for Magellan. And then if things start getting that expensive, and space is even a whole nother thing. I mean, the instrument budget roughly for the near-infrared camera for the James Webb Space Telescope is about $130 million. So what does that mean? That means I'm not going to be able to take a first-year graduate student and just throw them into the lab with a screwdriver and a hammer and say, yeah, go adjust that thing, because all of a sudden, they put the screwdriver through the detector and $130 million goes away. So as things got more complicated, number one, you could not be a master of everything. It's just impossible. And things got so expensive that the nervousness and the professionalism and the management of having to navigate a project that complicated and expensive made it less accessible for students to get their hands dirty in the lab with a project. So that's unfortunate. Big, expensive projects also take a very long time. So one example I think you might be interested to hear about is the camera for the James Webb Space Telescope. I started going to meetings and serving on a committee to design, or at least discuss, the attributes of instruments for that telescope in 1997. And we finally wrote a proposal. I was part of two proposal teams to build, or ended up being part of two instrument teams. In 2003, I think, we were awarded the contract. And so it takes 10, 15, 20 years to build an instrument that complicated. And frankly, the near-infrared camera, NIRCam, which is being led by the University of Arizona by my wonderful colleague, Marcia Ricci. She's like John Monnier. She's one of these, real world leaders in her field. And we hosted her for the Muller Prize right before the shutdown here at U of M. She's fantastic, and she led that whole project. She almost did it all by herself, but she worked with industrial partners. So we worked with Lockheed Martin. And it certainly wasn't the case that we got to go into the lab and play with little bits of that instrument. But I was there as a kind of an advisor for much of the science that we wanted to do and the scientific requirements that the instrument had to make in order to fulfill its promise and its dream. And that project took a very long time, and a project like James Webb in particular was unique. This is a proper use of that word. I think the astronomy community has certainly never had a segmented telescope that needed to deploy on orbit, where astronauts were not going to come like Hubble and revive it or refresh it occasionally, and at a level of tolerances that were really unknown. People often ask about the cost overruns for James Webb. And while they're challenging, and certainly one can point to mistakes that were made along the way, it is very difficult to know exactly how much something will cost that's never, ever been built before. And whenever you face a challenge that you need to fix or a problem, I have tremendous admiration for the engineers and technicians who overcame all of those hurdles over the last 20 years. But it is an expensive proposition, there's no doubt about it. I can also say that sometimes the uncertainty of funding, or the unknown contributions of partner countries, or the management and the way such a complex international project gets brought together, adds additional cost that doesn't necessarily buy value. But if someone came to the right group at the beginning and said, we'll give you exactly the amount of money you need for it, you don't need to have reviews, you don't have to do any bureaucracy, you should do reviews that you think you need to do technically, et cetera, et cetera. I don't know how much the telescope would have really cost if it had been done perfectly, but the chances are it wouldn't have been done perfectly because it had never been done before. And it's just very hard to value. But I think it has taught us that as we got to these bigger and bigger things, and of course the space game is very different, but we're getting there with ground-based instrumentation too. There's a level of professionalism and a level of redundancy and a level of design checking and rechecking and triple checking, and management of thousands of people who cannot be co-located, and how you design interfaces and manage the design of those interfaces. All of that sort of may sound boring, is like management 101, but it gets to be hugely important to the successful completion of a project that's of the billion-dollar scale, or that's going to last over decades, which can be more than the professional lifetime of people who come and work on a project and move elsewhere. So I have to say, as things have gotten more complicated, it's gotten harder to involve students in the nitty-gritty and to connect the dots between the technical knowledge you need, between the physics, basic research you need, between the computer simulation you need, the software development you need, etc. I'm sorry, I'm answering a very expansive question, but I think you also asked about computers and their role in this process. That is multifaceted. I would say I still gravitate towards new instruments where the basic physics technology itself can create an order of magnitude improvement. And that's generally not going to be the case for a computer. A computer is going to help me extract very efficiently the absolute amount of information that's really contained in those images, and my ability to do Bayesian analysis and to use proper statistical inference, which I have to tell you has grown by orders of magnitude since I started as a student. I published papers doing things 20 years ago that I would never be allowed to do today.
Right.
One of our astronomy representatives for the Michigan Data Science Institute, Chris Miller, is a real expert in some of these statistical techniques. And Oleg teaches a course in computational astrophysics using techniques that I could have only dreamed about in the early 90s. But now, yes, you have to use this kind of state-of-the-art approach to extracting information. And I guess my feeling is that software development has saved us orders of magnitude in time, just absolutely in time. Techniques have saved us factors of 2 and 3 in our ability to really pull things out. You know, you can't make a source appear in the detector if it's not there, but computers can help you very accurately know what your real errors are. And that is a huge boost to the field in terms of doing better science and hypothesis testing. But there is still a role for a new solid state material that can detect photons at a rate 2 or 3 times more efficiently than another one. And because the observations tend to go as the square of the signal to noise goes as the square of the exposure time, if I can improve things by a factor of 3, that turns into an order of magnitude savings on the telescope time. And that's a big, big deal. And I get very, very excited about helping make those leaps go forward.
So compared to before, when we were talking about citizen science and people using this transit method where they can see the light curves on the internet and kind of locate where those are as the exoplanet passes in front of the host star, what other techniques do scientists like yourself or other astronomers use to detect these exoplanets? And like, to what accuracy can we detect these wobbles? And what's the future of exoplanet discovery and studying their atmospheres?
So the first thing was radial velocity. That was the first discovery in 1995. And that was done with a spectrograph that had an accuracy of a few meters per second, whereas 1 meter per second is about human walking speed. That's about how fast we can measure with our Doppler radar gun the speed of a star as it is moving in response to the dance of the orbit of the 2 bodies around their common center of mass. So as the planet moves one way, the star is moving another. So we're indirectly detecting a planet using radial velocity, like your Doppler radar gun if you get a speeding ticket on a highway. The transit technique, as you mentioned, is the diminution of the light as the planet goes in front of the star. And that to detect an Earth-like planet around a sun-like star, you would need a spectrograph with a spectral resolving power for radial velocity that was about 10 centimeters per second. So a full order of magnitude better than human walking speed. The transit technique to detect the shadow of an Earth passing in front of the surface of a sun, you need about 10 or 20 parts per million in the accuracy of the photometry. So you're measuring brightness changes at about 10 parts per million. That is really hard. It's practically impossible to do from the ground, which is why space-based observatories like Kepler, like the TESS mission, and like the recently launched Swiss CHEOPS mission are done in space without the corrupting effects of the Earth's atmosphere, and other special techniques to get around weather and clouds and things to do precision photometry. So hopefully, starting now and going forward, we'll have the accuracy to measure the radial velocity shift of Earth-like planets around sun-like stars, but then we need to wait for the orbits. So an Earth-like planet at 1 AU takes a year to go around its star, and you probably want at least a few orbits before you can say you've confidently detected something. So the technology is there sort of starting now, and going forward around bright stars, we should be able to start seeing those discoveries accelerate again. The transit stuff is just going wild with the space-based observatories and ground-based complementary ones too. I do direct imaging. And this again comes from my heritage or my background in infrared astronomy and studying star and planet formation. In the mid to late 90s, we were pushing to find brown dwarfs in star forming regions. These are objects below the minimum mass where eventually a star can fuse hydrogen into helium in its core and have its own nuclear furnace, an energy producing source so that it can shine. Brown dwarfs are stars that are too small of a mass so that they can't convert enough potential energy into internal energy in their core to get the temperature high enough to sort of kickstart those nuclear reactions going. And that has to do with nuclear physics and the gamma curve and so on. But to try to keep me on track here, we were looking for brown dwarfs and say maybe trying to find a 10-million-year-old 30 Jupiter mass brown dwarf in star forming regions. The technology to do that is not so different from trying to take an image of a 1 Jupiter mass planet closer to its host star. So I was kind of on that track, and it was an easy pivot for me. What has revolutionized the ability to do direct imaging, which is looking at faint things near bright things, is adaptive optics. This is the ability to take out wavefront errors that are introduced by the Earth's atmosphere and try to get back those perfect plane parallel waves of wavefront from our star and planet, and do that by modulating the optics in our system so that we can reach the ultimate diffraction limit of a telescope, the so-called Rayleigh limit, which is proportional to the wavelength of light you're observing divided by the diameter of the telescope, lambda over d, as we call it. And the ability to do that can get you, for an 8-meter telescope, around typical nearby stars that are young enough that we could still see planets from the glow of their gravitational contraction. We can probably do that around at about 30 AU, maybe 20 AU, maybe 10 AU for the very nearest systems. The nearer by my targets are to my telescope, the better the physical resolution is of how fine I can resolve things. Now, if I told you I could see a Jupiter mass planet at 20 times an AU, which is the mean distance between the Earth and the Sun, I wouldn't see Jupiter that way. Our Jupiter is at about 5 AU, 5 times the mean Earth-Sun distance. So if there was a Jupiter mass planet at about 20 AU around a star at 50 parsecs at about 30 million years, I could see it. I could take a picture of that thing. So what we're doing is designing experiments using state-of-the-art adaptive optics on the world's largest telescopes to try to resolve Jupiter mass planets around sun-like stars. And so far, we've detected about a dozen of them. And that's not as many as the 3,000 plus, 4,000 plus planets that have been discovered from transit. So we're kind of the poor relations here. We have not detected so many objects. But what we are useful in doing is placing upper limits or measurements of the occurrence rate of planets at large orbital separations. And what we have found in those kinds of studies is that planets that are really, so imagine that the star is here on my left hand. Planets that are really close to the sun are there, but not so common. And as I get out to distances of 2, 3, and 4 AU, that seems to be about the peak in the orbital distribution. And then we start to see it falling off again, which is bad for me because I don't get to detect a lot of planets. But we design our experiments to measure that distribution. And just in the last 2 years, we've been able to point out that the peak in the distribution of gas giants around sun-like stars, M dwarfs, and I'm starting to also believe intermediate mass stars, is all about 3 times the mean Earth-Sun distance. And that's kind of a new discovery of a new fact about the distributions of exoplanets, which we couldn't have done without direct imaging. More fun is to detect something. And if we detect something, we can take spectra of those planets and analyze their atmospheres. That allows us to guess the temperature. That allows us to look for the atomic and molecular fingerprints of different species in the spectra of those bodies, and then look at their composition to learn how much carbon nitrogen and oxygen they have in their atmospheres. And that is another handle. The gross demographics also should be a predictive outcome of planet formation theory, but also what planets are made of is a powerful constraint on planet formation theory. And ultimately, I just really want to know how planets are formed. How common are they of different types? And again, ultimately, we'd like to know how common potentially habitable worlds are elsewhere in the universe.
Mm-hmm. And I know you mentioned earlier that there is a lot that goes into funding different projects. One of the things that we found was the Decadal Survey. So essentially, it's kind of a committee that overviews and distributes a lot of the funds that's like overlooked by NASA and the National Academy of Sciences. So how does organizations that distribute funds like the Decadal Survey impact the research that you're doing, and how can it change the field of astronomy, and what's more prevalent and what's not?
So let me clarify.
Mm-hmm.
The National Academy runs the Decadal Survey, and this is requested by Congress, and the document that is produced in the end goes to both NASA and NSF. It is a plan. It is a recommendation. It does not give out funding, but it tries to set priorities from the community. And generally, the administrations that execute, and the Congress that appropriates the money, and the executive that tries to execute the appropriations, tries to listen to the recommendations of the Decadal Survey. And that's a tradition that goes back to the 1960s. Astronomy did its first Decadal Survey back then. I think we're on our 7th now that we're doing now. We tend to do them every 10 years. I think the first one was called the Field Report from George Field, who led it. And this wasn't generally done by other disciplines at the time. And by the 80s, 90s, and zeros, other disciplines got online and decided that this was actually a really good idea to let the community kind of bubble up its own plan, give it to the government, and then hopefully the government would execute the most important parts of it. The government can and does sometimes disagree with the survey. They try not to, but there can be reasons down the line where they are unable to, for whatever reason, maybe they don't have enough money or whatnot, so they need some guidance, but they can't always follow it to the letter. I'll also just point out 2 things. Our whole national science funding infrastructure only arose out of the ashes of World War II. And there really wasn't a thing like government-funded research before World War II. People saw the value of it in trying to bring the economy of the world back. And obviously, there were researches that were related to defense that became part of that research complex as well. The other key thing that was before your lifetime was the Apollo program, and before mine too. I was barely alive when people landed on the moon. But the extraordinary amount of science funding that started really our space program in the 60s is unparalleled. And if you extrapolated the rate of growth of science funding from the 1960s forward to today, we would totally have to be mining asteroids to have any sort of productivity to fund a research enterprise like that. I mean, it was just off the charts. So it had to flatten out. And what I try to remind people as we go through each decadal survey is there really is no normal of science funding. We're all just sort of figuring this out in the last 70, 80 years. And different cultures and societies will place different priorities on different things. And that's reasonable and right and good that they do that. And we, as scientists, will have things we want to do, and we think they're aspirational, and we think that they can inspire. We think that they can help attract people to science and education, which is healthy for all of us. And they might even have unintended practical benefits down the road, which we all benefit from, which we can come back to in a minute. But the survey, as it is constructed by a plan that NASA makes with the NSF and DOE and other funding agencies. And they collaborate with the National Academy of Sciences, which is this select group of self-selecting people, which is dominated by the older, more accomplished, more senior members of the community, which, by the way, is not the most diverse and most representative body in the field. And they get together and make a plan for the survey. They pick chairs of the survey, And then the survey chairs get to then pick their central committee that's going to help them execute the survey. And then there's several subcommittees that are formed on different science areas or on different wavelength regimes or different techniques. And all of these subpanels are then populated. Reports are received. There's a call that goes out for white papers. This is a funny term, and I had looked up the origin of it, why they're called white papers. And I can't remember the answer off the top of my head, but I think it's on Wikipedia. And people write these kind of policy documents. I study exoplanets, and so we want to explain to the Decadal Survey how important it is to study demographics, as I was explaining before, the distribution functions of these planet populations. And so we write a paper about how important that is for all of science and for exoplanets in particular, and what capabilities and facilities we need to make major progress. And we're given rules, like the paper has to be due on 2019, August 3rd, and it can't be more than 12 pages long, and it has to be in this format. And so hundreds and hundreds of these white papers are written, and they go to these panels, and they're read. And then the panels can invite different groups in to pitch ideas or to propose projects. And then each of those subpanels writes a sub-report, which then goes to the central committee. And it's a huge, huge effort. It involves dozens to hundreds of people, and literally tens of thousands of members of the community involved in writing white papers and different things. Town halls are held at the American Astronomical Society meetings, which are not happening face-to-face now, but certainly happened in January in Hawaii. And so they try to keep people informed. They try to gather feedback on process. There are panels about the state of the profession, so that people have an opportunity to complain about the unhealthy elements in our profession, how they feel like it doesn't really promote healthy work lives or family-friendly work environments, or that makes it difficult for underrepresented populations to really get into the field and fully contribute in the most important way. So there are lots of voices that come into the Decadal Survey, but ultimately it comes down to sort of one 150-page report, which has a series of recommendations. And they can't touch on everything, and they certainly can't get everything right. They also have independent costing estimates for all major projects, because they don't want to, suppose you had $1 trillion astronomy budget for the next decade. Well, you can do everything. You don't have to make tough choices. But what the charge to the survey is generally to rank order things, and not to say, have to fund this, don't fund that. They're really just meant to prioritize things, because we don't really know how the budgets are going to go down the road.